In order to save money 3D printing this part myself for 85 cents, I spent $35,000 on this tooling to injection mold them instead. Let's talk about why your preconceived notions about injection molding are probably wrong, what it takes to actually do it from someone who did, and also why on earth I would make this switch. One of the #1 questions I get asked when I tell people I 3D print products is, why would anyone have a room full of 3D printers? Why not just use injection molding? How can 3D printing even be competitive in today's market? To be fair, those comments are usually from someone who really doesn't know anything about 3D printing. But since I have now gone through the evolution of production 3D printing to production injection molding for just a couple of my parts, I thought it might be interesting to share my experience and to do my best to dispel any myths or assumptions that are floating around out there. But I don't expect you to just take my word for it. I sat down with Zach Allen, the CEO of Plastic Designs Incorporated, who is a legitimate ninja in injection molding. PDI also is my production partner who guided me through the process of redesigning for injection molding, managing the mold manufacturing process, and now physically runs our production injection molded parts. More on that in a bit. Most people, myself included, just assume that 3D printing is cheap and injection molding is expensive, right? But the truth is, if you look around you at any given time during the day and you see a piece of plastic, could be sitting at your desk, in your kitchen, or even in your car, I can almost guarantee that it was injection molded. It is far and above the most common way to produce plastic parts. So if it's so widely adopted, how could it be so expensive? Well, as you may have guessed, it has to do with the quantity of parts. Because it's not that the injection molding is expensive, it's the upfront cost of the tooling or the molds that is the expensive part. So unless you plan on injection molding a ton of parts, like consumer electronics, kitchen utensils, or automotive parts, to spread out that initial cost of that tooling, it seems hard to justify. But what is that magic number of parts where it makes sense? 1,000, 10,000, 100,000? A million parts? You might have a number in your head, like I did, but the real answer might surprise you.
I think one of the biggest misconceptions that I run into is that it costs tens or hundreds of thousands of dollars to make a mold. Yes, certain molds might if the job requires it, but we've made a mold as cheap as I think $3,500. We've made a couple around $5,000. So it is possible to get into injection molding at a low capital investment scale. Also, another misconception is that you have to be at super high volumes. You have to be hundreds of thousands of units. And ideally, yeah, that's great to have that level of volume, but it's not always required. Some molders might have requirements like that, but we've got customers who order a couple hundred parts a year, 250 parts a year. We've got other customers who order tens of millions. So it's possible. You just have to find the right partner to work with.
Before we get too far down the rabbit hole, let's start by looking at both processes from a high level and how they work. Look, 3D printing is awesome, and we all kind of know how it works, but it's helpful to look at the big picture. Before you ever load up your printer with filament, that filament needs to be produced and extruded. And the production of thermoplastics starts at a chemical plant, which uses giant equipment to combine different raw materials into a molten plastic. This plastic is then pushed through a sort of spaghetti die and chopped up into small pellets. Giant sacks and totes of these pellets are then shipped to customers around the world in train cars and semi-trucks. The bulk plastic pellets finally arrive at a filament manufacturer's extrusion line and are loaded into a giant hopper, mixed together with additives and color, heated up and extruded once again through a circular die this time as a long uniform strand, where it's finally wound up on a spool which produces the filament we all know and love. So the raw material you use to 3D print has already gone through its own production journey and actually been extruded twice already. And this is important when we start to understand the impact on material cost and on the final cost of the 3D printed parts themselves. And then when it comes to printing, we obviously need to generate a print file, send it to your 3D printer, and press print. The printer then heats up the filament, extrudes it for the third and final time through a teeny tiny hot nozzle, and precisely places that molten plastic on top of itself in very thin layers until the part is done. Whew. Which leaves you with this part, and an all-in printed cost of around 85 cents. The cost of just the material is somewhere around 25 cents, but factoring in everything it takes to print this thing increases the cost by about 3x. If you don't believe me, check out the video I did on pricing, where I break this down to see what I'm talking about. Now, let's look at injection molding. Oddly enough, the start of the journey is identical. Pellets are produced at a chemical plant and then shipped to the injection molding facility.
Basically, what happens is plastic pellets, or plastic resin is how it's called in the industry. That's just the raw material. It's just like a little cylindrical or spherical piece of plastic that gets brought up into the barrel, where there's like an auger screw inside the barrel, and the barrel is kept at high heat. Think about like 400 degrees Fahrenheit. The screw rotates, and that causes like friction heat on the plastic, and that also kind of like helps get everything mixed together really well, especially if we're adding colorant in. And then from there, that gets injected into the mold, and then the mold opens up after the part cools inside the mold, and then the part's ejected.
It sounds simple, but the molten plastic has to be forced into these molds under extreme pressure, on the order of tons or even hundreds of tons. For this reason, the injection molding machines are quite large and expensive, and the molds themselves need to be able to withstand those extreme forces.
Yeah, so I mean, we have a range of machines. We've got small, what I consider small machines. There are certainly smaller, but we go from 90 tons up to 880 tons. So we run your products in a 200-ton machine, but we could probably run them in a 90-ton machine. So that's kind of, they're on the smaller end. We have one product that's about 4.25 pounds, and it takes every bit of 880 tons to keep the mold shut. So
now, when I say mold, here are some examples of what that looks like. They are the interchangeable part that's loaded into the injection molding machine. Big chunks of steel with precisely machined shapes in each side that, when sandwiched together, produces a perfect physical void that the plastic fills and then hardens in. Once the plastic is set, the parts are ejected out of the molds, usually with little pins that push in certain areas. Then the mold closes back up for another shot before the cycle repeats over and over again. The design and production of these molds are a science and sometimes even art of their own. Depending on the final part geometry, they can get really complicated with internal moving parts, special cooling channels, and even different plastic delivery systems.
So the feed system can be there's a few different methods for a feed system. There's the cold sprue and cold runner, and that's what we've got on your molds. So the plastic leaves the injection barrel and then goes into a cold sprue, and then that forks off into the runner, and then that enters the final part through what's called the gate. So that's kind of your traditional, like that's what a lot of molds have. Then there is a hot runner, which keeps the molten plastic like right at the part. And so every time you inject, like the plastic is right there ready to go. There's nothing to trim off after the mold opens. Then one step further is a valve gate hot runner. And sometimes with that thermal, it's called a thermal tip, the hot runner, that's just right there on the part. Sometimes, like if the plastic isn't heated just right, or if you are trying to run a really fast cycle, when that opens up, if there's still kind of molten plastic right there, it'll drag like a string. Like think of like a cheese pizza dragging that string. We ran into that a lot on one of our products, and so we changed it to a valve gate hot runner system, which has a pin that actuates forward and backwards. So it opens up, lets the plastic in, and then it shuts like an actual pin shuts that hole, and then you end up with like no gate vestige whatsoever. And so that giant mold has a valve gate system in it as well, which is really nice.
Now, getting these molds initially designed and made is actually the biggest cost driver for getting a new part injection molded. Zach mentioned that there are times when molds can be less than $5,000, but generally they average probably around the $10,000 mark and can go way up from there. The actual plastic used and machine time needed for injection molding is very trivial and almost always less than 3D printing. Part of the reason for this is that there's no intermediate step and additional cost of extruding into filament, packaging that up, shipping that out, which is then marked up and sold to you. For this reason, the true raw material cost of injection molding is always much lower per kilogram than a spool of filament will ever be. So after the molding process, you end up with a part like this, arriving at a total cost of about 40 cents. Well, kind of. Remember, there's that pesky upfront tooling cost to consider, because to get to the stage of holding an injection mold part, you would have had to have already spent a bunch of time and money on the tooling. For round numbers, let's just say the tooling cost was $10,000. If I just needed to make one of these parts, the unit cost of having this injection molded would be $10,000.40. A little steep. 3D printing one of them would obviously be much better option and would be significantly faster overall as well. But what if I needed 1,000 of them? Well, you take that tooling cost and spread it out evenly amongst the parts, leaving $10 of tooling cost per part plus the 40 cents of material, leaving a part cost of $10.40. Still pretty expensive. We're still an order of magnitude more than 3D printing them. Plus, I bet even with a single 3D printer, you could print 1,000 of them faster than the total tooling and production time, and at a lower cost. Injection molding still probably doesn't make sense, right? But you can start to see the cost curve come down as you increase quantity. At 10,000 parts, the injection molded version is only $1.40, which is much closer to the 3D printed cost. But now in order to 3D print that many, you would need more printers and more man hours to manage them. And that was the big aha moment I had in my business. Though the part cost economics were important, freeing up capacity in my print farm created even more value for me. Because you see, we weren't just printing this one part, we were printing a set of these 3 parts. They're basically adapters which are common amongst a lot of the products that we sell. So as we grew and the overall usage of these standard parts grew, the time, energy, and printers we needed just to keep up with the demand got a little out of control. But the prospect of injection molding was kind of intimidating to me. I had some high-level knowledge and had even been around mold shops before, but I didn't know the first thing about what it took to get started.
So you're the expert in 3D printing and what the end use is for the product. On our side, we're the experts in actually manufacturing it in injection molding. So I don't expect you to know how to do draft angles and how to make it moldable. So that's really where I try to offer value to the customers, because I can understand what their requirements are and then offer suggestions of draft angles and slight design changes to make the part easier to produce and cheaper to produce. That, you know, if you had decades of injection molding experience and came to us with a perfectly manufacturable part ready to go, that's great, but rarely do we have that. Even people who have injection molding experience come back with something that needs a slight modification, or even sometimes our tool builders will come back with modifications that we haven't even thought of. So it's really just the whole partnership stream that we try to help out where we can, because everybody has something to learn and different strengths. So that's where we try to offer value there.
So did I snap my fingers and jump right into ordering a mold? No, of course not. But here's how I did it. First, I established with numbers and data that it really didn't make sense for me to 3D print these myself anymore. So a temporary easy button was to farm these out to a larger print farm. Yes, I solved my 3D printing problem with 3D printing. I held off on doing this because I just assumed it would be incredibly expensive, but I was actually shocked to learn it wasn't that much more than I was making them for. I reached out to Gabe at Slant 3D. Yes, the dude you've probably seen around YouTube that is most definitely not me, but people assume is me. He quoted me a really reasonable price, and we started getting a steady, reliable stream of parts from them. This freed up a lot of my printers to absorb spikes in demand and to allow for new products to get launched, while also reducing the overall labor burden required. Yes, of course, I was paying a premium for this because Slant 3D has to make some money too, but I was happy to do it. In parallel with this, I started working closely with Zach at PDI on the redesign of my parts. Because it turns out, just like 3D printing has design considerations, so does injection molding.
One of the things that jumps out a lot is like the wall thickness. So in 3D printing, you don't really have to worry about the wall thickness, but that does matter in injection molding. You want a uniform wall thickness where you can. And like I said, it's not really something that you have to worry about in 3D printing. 3D printing is great for making a lot of different complex shapes, which might be challenging for injection molding. But as we learned with your project, even though it seems like really complex to have threads on the inside of a mold or on the inside of the part, it didn't end up being a terribly complicated mold, and it was pretty easy to execute.
What was cool is that Zach actually helped me improve my parts. We went from an external thread, since it was easier to print, to an internal thread, which was actually much easier to use in practice. We also added a more robust locking feature and some nicer text. But another key benefit of injection molding, thanks to its long established history in the manufacturing world, are the seemingly infinite material options available.
Material options are pretty wide, because you have a handful of generic, common types of plastics, but then even in those types of plastics, like let's just talk about ABS, there are probably thousands, if not, I don't know, hundreds of thousands of different grades, specific types of ABS that all have different material properties. So it can be really challenging to pick the exact same, the perfect material. But if it's a general purpose application, you've got like polypropylene, polycarbonate, ABS, polyethylene, um, polystyrene, different grades of polystyrene. Like high impact polystyrene is one that we use a lot. Um, there's so many different ones. You even have like exotics, like Ultim, which is PEI is also another name for, or Ultim is the trade name for PEI, and that's an extremely high heat material. We have a product that we make in Ultim, which has its own unique challenges, but really the choices are pretty endless with injection molding. And with 3D printing, the material availability has come such a long way in the last even 5 years. You've got, your generic like PLA and PETG, and ABS, of course, but then, you're getting all the carbon fiber filled materials and things like that. So I'd say, like, as far as material availability, injection molding has, like you said, a lot more options available, um, and it's not as limited to like what your environment is. Like ABS is tough to print on just like a cheap desktop printer, maybe if you don't have an enclosure. But with injection molding, we don't really have those limitations.
And then to go a layer deeper, it's not just about the materials themselves, it's the material properties too. The same part 3D printed in ABS is very different than the same part injection molded in ABS.
With 3D printing, you obviously have the layer lines, or if you have, if you're doing an FDM print, um, but you're essentially taking a somewhat molten material and kind of squeezing it together. Whereas injection molding, it's starting off as a completely molten state, and is homogeneous throughout the part. It's completely the same, essentially the same material structure throughout the entire part. So if you have layer lines in the wrong direction on a mechanical part, it is probably going to fail along those layer lines. Whereas injection molding, it's not really prone to those layer line type of splits. You might have sharp inside corners that end up cracking on an injection molded part where they didn't on a 3D printed part, and vice versa. So I think you have a little bit more leeway with, or you can end up with a lot stronger parts with injection molding. You can get away with thinner wall sections than you could compared to 3D printing, um, and a lot more complicated structures as well with injection molding.
So at this point, I had the new parts redesigned, and instead of the original PETG, we were gonna go with a much stronger molded ABS. But before I committed to this new design, I needed to be positive everything was correct and that it fit with our existing parts. Look, FDM printing is great, but it doesn't quite have the resolution and accuracy of something like an injection molded part. Plus, it doesn't do well with tiny details and thin wall sections. So I turned to resin. It was fun learning a new 3D printing technology I had never used before during the course of this transition. And I picked up this Haygears Reflex RS combo. Being a complete noob, it was pretty straightforward, and I was printing my first part within a couple of minutes. If you are as clueless as I was, here's how it works. You slice your part just like you would for anything else, but orienting the part on the print platform is a bit different. I chose the option to reduce the number of support contact points and ended up with this. Then you load up your printer with a bottle of gloop, not filament, and let it slowly fill up. You can then send the file over and watch basically nothing happen. There's only one axis of movement on these type of printers since all of the X and Y magic happen under the pool of gloop on the screen. So you just see the print platform pulse up and down every once in a while, which isn't all that exciting. When the part is done, you don some gloves and scrape it off the platform ahead of the next step, which is washing. There's still a bunch of liquid resin and gloop covering your part, so it needed to be rinsed in isopropyl alcohol. After a satisfying swish in the bath, this part can be removed and placed into the last step of the process, the curing station. This little easy bake oven warms your part and evenly exposes it to UV light, fully curing the part and bringing it up to its final mechanical properties. After you trim off the supports, you're left with a smooth, precise part lacking any real visible layer lines. The process is messy, but it's a really cool tool, especially when testing exact part fit for injection molding. But this was my original part, so I went ahead and printed the newly designed part and tested the fit. After a couple of iterations, I felt confident in the final part design, and I bit the bullet and signed the contract for the mold. So let's talk numbers. I mentioned earlier I produced this part for 85 cents, but the full set of 3 parts, the transition, the medium adapter, and the large adapter, cost me a total of $1.63 to print. When I farmed them out, I paid $3.20 to get that same set 3D printed by Slant 3D. Up until this point, they were produced in black PETG. After redesigning the parts, the injection molded cost per set of parts, in black ABS this time, is $1.24. So about 19 cents cheaper than I was 3D printing them myself for. And now it's in a much stronger material as well. But of course, what about the mold? For what ended up being a total of 2 molds, including a really cool screw mechanism to produce those internal threads, I paid just over $35,000. So my cheap parts just got a whole lot more expensive. Luckily, the volume of these parts we use has been steadily growing since they're fairly common amongst all the products that we sell. So based on our current and projected volume, the estimated ROI, or return on investment, is about 8 months. And this is based on the cost of outsourcing them since I decided these lower value parts were not worth us printing anymore.
So for example, your core products are the dust collectors, and those have really complicated shapes, and you are making a wide variety of them. Those, I think it makes so much sense to keep as 3D printing because you're a lot more agile to make changes, make updates, have really complicated geometries to fit around somebody else's structure, the saw manufacturer structure. Whereas the hose adapters, since those are all the same across the board and you're making so many of them, I think that is a clear indicator that it's a good opportunity to go to injection molding because it's the same part. You're chunking out tons of them, and if you can manufacture them at a lower cost and maybe more reliable quality, then I think that's a win-win. And I think that's kind of where I would lean to make that trade-off.
In my particular case, the economics of injection molding these parts worked out in my favor. But like I mentioned earlier, one of the biggest takeaways I had going through this process is to leverage the power of 3D printing where it is most valuable. I say this over and over again throughout the course I developed, that just because you can print something doesn't necessarily mean you should. If 3D printing it adds no value long term, then you should seek the best way to produce it.
You're not 3D printing your hardware. You're not 3D printing nuts and bolts. You're not CNC cutting nuts and bolts. You're buying those off the shelf because it becomes that reliable, consistent stream of products. That's not the value add for your business. The value add for your business is the actual end, the dust collector on the saw. This is just a way to get the dust from that point into the customer's vacuum system. So that's why this is not your main value add. So that's when, if you can outsource that to a more efficient, maybe more streamlined manufacturing process like injection molding, that's when it makes a lot of sense.
It's been amazing to get a big shipment of these in and not have to worry about producing them anymore. There's definitely an opportunity cost there. Now we get to focus on higher value parts in our print farm and launching new products, most of which are actually fantastic fits for 3D printing.
Yeah, and I mean, think about it. If some of the more complicated parts that you manufacture, that you print, if you wanted to injection mold them, that mold could cost somewhere in the $100,000 range. So if you have 10 different products, you're talking about $1 million of capital investment. Can you imagine how many printers and how much product you can make for $1 million? So 3D printing absolutely has a place. And just because it's plastic, it doesn't have to be injection molded. If you can manufacture it more efficiently, if you can get started with spending a couple $100s on printers, like these days printers are so cost effective and really attainable. So it makes a lot of sense for people starting out to 3D print. And then if you're growing and scaling and want to talk about injection molding, great, let's talk. But otherwise, I definitely don't deter anybody from doing 3D printing.
Now, some of you out there may think that none of this applies to you or will ever apply to you. And I was right there with you. I didn't think my little 3D printing hustle would ever be large enough to even entertain injection molding. But remember, I'm not a giant print farm with thousands of printers. We only run about 60 machines. And even at that volume, there are opportunities that make sense to injection mold.
It makes a lot of sense in your situation where you have a print farm where you really are you're producing, you're mass producing. Essentially, if someone's got one printer, 2 printers, it's going to take a long time to make that leap make sense. So depending on who your target audience is, somebody's well, I normally making 10 a day. I can't spend 20
Right.
grand on a mold. But
Right.
but then like you're also like not talking to that same level of customer. It's more so if you're in like 30, 40, 50 printers, maybe it's time to think about injection molding, but and not as a way to replace your business, but I think like what you're angling is to just shift the non-value add products to somebody else who can manufacture more efficiently.
I've always been a manufacturing nerd and geek out over this stuff. When I was on the call with Zach, he talked about automation and how my parts specifically were benefiting from it.
So one thing that we've been trying to do a lot here is automate those processes. So right now, your parts are just falling out of the mold onto a conveyor belt that then gets brought up to the operator who boxes it. But next time we run it, we're gonna have a robot taking those parts out of the mold and placing them on a conveyor, and that makes it a lot easier to handle them, to sort them, and then to package them. So that's the automation is a really great way to streamline the process even more. And we do a lot of that development in house. We don't outsource any of the automation because frankly, it's really expensive to make automation if you outsource it because they want everything to be 100% foolproof, and most of the time that's not necessary. So we're able to make some pretty simple end of arm tools, end effectors, robotic setups to handle our customers' products and make the process more efficient.
And in a full circle moment, since I used to help manufacturers like PDI use 3D printing to improve their processes, I asked if they were using any 3D printing in their facility to help with that automation.
On our high volume line that makes 350,000 parts a day, we have um, we have 3D printed gripper fingers that touch every single part that comes out of that machine. So we rarely have to change those 3D printed parts out, but the reason we love 3D printing those is because if something goes wrong, if there's a position something out of place and the robot crashes, instead of the expensive stuff breaking, the cheap 3D printed fingers break, and then we can just swap them out and carry back on. I think some people might think that they butt heads, like it's either injection molding or 3D printing, but it's not like at all. Like they're just different manufacturing processes that can work together, and they both have their places in the world of product development.
So there you have it, an actual example of a 3D printed part moving to injection molding with numbers to hopefully demystify the process. Hopefully that was helpful. Let me know what you think. And if you're out there thinking about injection molding opportunity, I can't recommend PDI enough. I'll leave some links down in the description on how to get in touch with Zach and his team. If you want to check out the full conversation Zach and I had, that will be available in the Print Farm Academy course as a bonus piece of content. Happy printing and molding out there.